let's talk about how to determine the number of electrons that have been gained or lost in a redox reaction. And this might be because you're trying to write half reactions. It might be because you're just trying to answer the question, a question about how many total electrons did this particular one gain or lose. So let's talk about how we would do that, and then we'll look at a couple different examples. So step 1, assign oxidation states. So assign oxidation states, right? So let's do that down here. We're going to assign oxidation states. This is probably a little bit more challenging of one than I would give for you to write a half reaction on. But I really just wanted to focus here on the iron because it gives us some good work to go off of and reinforces some of our oxidation states. So we're actually just really going to focus on the iron here alone. But we would often want to assign oxidation states to everything. So in this case, the oxidation state of an ion is the same as it's charged. So the oxidation state of iron on the reactant side is +2. The oxidation state of iron on the product side, however, is +3. So we see here that we've had an increase in oxidation state. Going to our little redox hieroglyphics that help us, we can see that it was oxidized. And then, of course, if you use our other memory tip, oil rig, that helps us know that oxidation is lost. So this iron atom has lost electrons. So we've assigned oxidation states and kind of interpreted them. Maybe that's a second step. We'll say and interpret, using the different tools that we have. So step 2, assume 1 electron for each change in the oxidation state. I'm going to say just oxidation. So what I mean there is, so here we're going from 2 to 3, right? So I think of it like a vertical number line, and we have pluses and we have minuses, and then this is here 0. So if iron was already up here at +2 right there, and we have a 1 movement jump to +3. So that's a change in oxidation state of 1, right? So that is 1 electron. So then in terms of if I were going to work on writing iron's half reaction, I would have iron 2. That would just be the name of this cation, iron 2. We'll just put that there for review. It tells us its charge. Iron 2 becomes iron 3. Oops, parentheses are not there. Iron 3 through the loss, and this is always a funny one. We don't say minus an electron. We say plus through the loss of an electron. I always think of it as if like it lost it, but it's just actually down on the floor by it, like you might lose a dollar bill out of your pocket. That helps me prevent using a minus sign to reflect loss. So we have iron 2 becomes iron 3 through the loss of 1 electron. And again, I know it was 1 because it was 1 change in oxidation state, going from +2 to +3. Now, the next thing I want to do, kind of the last thing, is consider if I've been provided the balanced chemical equation. So in that case, I see here that actually I had 2 iron 2 ions, and therefore 2 iron 3 ions that were created, and each of them lost an electron. So it's kind of like you want to multiply the coefficient you're dealing with by this number. So 2 times 1 equals 2. So this is then 2 electrons. And you'll notice for a lot of redox reactions, the number happens to be 2, but that's actually really coincidence. So you don't want to just assume 2. Because it's a bad assumption. There's no reason to assume 2. You want to assign oxidation states and interpret, assume an electron for each movement of oxidation state, and then consider the overall balanced chemical equation. So let's do the same thing, but for a molecular compound. So these are all molecular compounds as opposed to ionic. We have some ions going on up here, and they just are kind of present a different challenge. But we're going to do the same thing. Assign oxidation states. So the first one I need to always remember to do is my what I call single ladies. And that's because otherwise I'm going to jump in and give that one a -2 because that's what otherwise usually oxygen's oxidation state when it's in a compound. So that it's -2 over here in both of these locations, -2, -2 for oxygen. So I need to go in and identify a free element and give it an oxidation state of 0 right away. So then I see that hydrogen is not a free element on either side. And so hydrogen usually has an oxidation state of +1. There are a few exceptions to that, but not ones we need to worry about in this class. So then I'm left with carbon. And carbon doesn't have a general rule. I'm going to have to solve for carbon on both sides based on the fact that the total oxidation state of all of this should add up to 0. So since I have 4 hydrogens, each which has an oxidation state of +1, hydrogen is contributing an overall +4 to the oxidation state. And I can usually see really quickly in a situation like that, since I only have 1 carbon, carbon's oxidation state must be -4. Because -4 and +4 together do make 0. Now over here, this is a funny one because my brain really jumps to 4 really quickly again, and I'm like, wait a minute, it wasn't oxidized. But let's double check. So I have 2 oxygens, and each one is -2. So the oxygen is contributing an oxidation state of -4. They should total up to 0. Now it is 4, but it's +4. And there's a big difference between -4 and +4 on a number line, right? That's a big jump. So this is definitely a redox reaction because I see 2 changes of oxidation states. Carbon's oxidation state changed, and oxygen's oxidation state changed. Divided up in a couple different places. So I have assigned oxidation states, and now let's interpret them. Let's use our symbols as reminders. This kind of just takes our brain out of the picture a little bit. We don't have to think so hard about, okay, who did what? So oxygen goes from 0 down to -2. So oxygen was reduced. So that's a reduction, a decrease. And of course, I use my oil rig. Rig reduction is gain. So I know that oxygen gains electrons. Now, by default, I know that carbon must have been oxidized, but let's also interpret it. -4 up to +4, right? So that's a movement up. So carbon, I might have said that wrong. I might have said oxygen again. Sorry if I did. Carbon was oxidized. So that's a loss of electrons. So let's determine then how many. So step 2, assume one electron for each change in oxidation state. And you guys can probably do this right in your head, but just in case, or even just for my own mental, let's start with carbon. Carbon is down here at -4, way down here, and it moves up here to +4, right there. Well, that's a movement of 8, right? That's a movement of 8, and therefore that's 8 electrons. So carbon loses 8 total electrons in this oxidation. Let's talk about oxygen. Oxygen went from 0, right there, down to -2, 1, 2. So we'll do like a squiggly line so we can see oxygens is different. So that's a movement of 2. So that equals 2 electrons. So 2 electrons. So this is a loss of 8 electrons and a gain, sorry, I might have said loss there, gain of 2. Now, however, we have to remember the last step. Consider the balanced chemical equation. Look here at our oxygen. Oxygen, 2O2 here, is actually a total of 4 oxygen atoms. So when I consider the balanced chemical equation, I have to consider that each atom of oxygen is going to gain 2 electrons. So therefore, it's a gain of 8 as well. So 2 oxygen atoms gain 8 electrons to create my products, my carbon and my oxygen. Whereas my carbon became all of this through the loss of 8 electrons. So there are 2 steps, well, 3 major steps. Assign your oxidation states and interpret. Interpret what was oxidized and what was reduced. That's going to help you know gain or loss. You need to assume 1 electron for each movement of oxidation state, and that can be big, like 8, or it could be small, like 1 or 2. But finally, consider the balanced chemical equation. Consider all the atoms that you have of that. And you'll notice that sometimes that means just look at your coefficient, like here. But sometimes it means look at both your coefficient and your subscript, like here. This is 4 oxygen atoms. Looks like 40. 4 oxygen atoms. So I hope that helps.